in this, we will be able to derive the system dynamics as algebra dealing with this segment equation. P dot we have as P by N. Mass flow is nothing but just by I guess, and since the mass is getting out of the very medium case. So this is the system dynamics. I'm not telling that this
The
is
stream link and I can just put it on the email
first dynamic.
to say that
Right.
it is functional.
In this, we have the states H, V, gamma, and M. These are the states. We have what is the control? What's the output of the operational control? Obviously, it is a control result along the state result. But what is the control? It is nothing but this alpha. Or otherwise, alpha plus gamma is nothing but the big channel, right? So when you are optimizing the present wave, what you are trying to do is to come up with the orientation of the thrust vector. In a launch vehicle, you really don't have an angle on the thrust mapping. Okay, whatever the engine is delivering, that's the thrust you get. We are not talking about throttle levels. Mostly, almost all engines are non-throttle. Thrust is fixed. So we don't have much of angle on thrust magnitude. All we can do is formulate the thrust angle, which is nothing but alpha plus gamma, thrust vector local horizontal. Is theta. So which present which which angle along the trajectory is what we are trying to operate. This is the system dynamics. We have the scale, we have the control. I'm not telling that this is the problem we typically solve. This is the simplified version of the problem. This is the simplified system dynamics that we can take. Okay, now we have the system dynamics at hand. What is the performance in this? What are we trying to optimize in a launch related optimal control problem? Can you guess? We have see ISRO has a fleet of launch vehicles. We have PSLV, GSLV, Mark, SSLV. We have S vehicle right now. So we have a launch vehicles. If you take any of these launch vehicles, can you guess what will be for a particular launch vehicle? What will be the lift of weight? Let's take GSLV Mark. Whatever I'm trying to, whatever numbers I'm putting forward here is available out there to the public domain and just trying to bring a perspective to it. Okay. See, GSLV Mark III has zero stage as two solid order boosters. Each weighs around 200 tons. We insert is just two. Then we have a core liquid state, which is called L110. Content, of course, it represents the mass of the fuel, 110 tons. Then above that, we have C20, that is cryogenic upper scale, which carries a fuel of about 25 tons. What was the payload capability of vehicle like GSL market?
Can check here something. You know, like it's doing inside storage security.
I'm not discouraging tax for this. CSLV Mark III can live a mass of about 5 tons with GPU. Okay, to the geosynchronous transfer. To the lower cognitive, say 8 to 9 tons, can lift about 9 tons. See, we are talking about 9 tons of payload at the expense of 200 into plus 110 plus 25 ton fuel plus the structural mass. Can you just imagine it? So, the expenditure that is actually happening in the process of a launch vehicle mission in terms of mass, so high. Okay, so obviously what we need to optimize is the mass that can be carried. You have to maximize the mass that can be carried with your. Okay. Uh, yeah. So I would like to bring another perspective here. How will you represent this in a mathematical because I cannot put just performance index into words, right? So when I say that mass of the orbit is what that has to be maximized. So trying to maximize M0 space. This is what top mass. So basically, integral T0 to TF dot dt is what we're trying to do. This is nothing but the mass expense, right? The return mass is fixed. So if you minimize the mass that is being ejected out of the rocket, ultimately you end up maximizing the payload, right? Now let me bring another perspective. Okay. Uh, you know what is impulse? What is impulse? Impulse. Impulse is thrust integral is impulse. Right. Integral of thrust is impulse. Do you know what is integral acceleration? Basically, these are measures of energy. Right. Integral acceleration, integral KD. This is a measure of acceleration, measure of energy that a launch rocket possesses. Right. Now, when we are telling that we have to take or maximize the mass to be taken to the orbit, ultimately the energy expenditure situations. That's it, right? Uh, Now, when you talk about the launch, let's say a launch vehicle that carries a satellite to low orbit, okay?
It's
The
too
actual
extreme quality one is not the same as very quality.
the unit is velocity, right? So a launch vehicle that actually carries a spacecraft to the orbit will contain an integral acceleration of about 9 kilometers a second.
4K.
9 kilometers a second.
Yeah,
But
go. Yeah.
what is the velocity achieved by a spacecraft in a lower orbit? It's of the order of 7.5 kilometers a second. Circular orbit will take the units of cube by r.
Okay.
Right? 7.5 kilometers per second. But actually, you are delivering 9 kilometers per second. Where does this 1.5 kilometers per second go?
Seems what
It is actually going towards their losses.
acceleration.
What are the losses? The major share of the loss
I think it would.
is gravity. One. And steering this. So when we are trying to optimize the space or the mass in the orbit, we are trying to minimize
I think
the
you are the
losses. So ultimately,
I just
this is
think
equivalent to intermediate minimizing intermediate minimizing
focus on
the mass expenditure is same as minimizing L1 law, first law of acceleration, and it is not same as
little bit greenness.
this is not giving minimum fuel expenditure. It is minimum control, but that does not guarantee minimum fuel expenditure. Now we have a handle on our system dynamics. And what is the objective function that we are trying to minimize? Now let me come to the other aspects. Where are we sending these rockets? We are sending these rockets to orbit, some orbit, right? They are the targets, right? How do you define an orbit? We need a definition to the target, right? How do you define an orbit? In classical orbital elements, Keplerian orbital elements, you can define an orbit using 6 elements, actually five elements. And the position of the spacecraft on the orbit can be represented using a sixth element. So, for to define the size of the object, we have semi-major axis, and shape of the object we have eccentricity, and the orientation of the object is determined by three angles. Comments. One is lamb. Longitude of the ascending pole. We have inclination. Then we have argument of variation. That makes it five, right? A, E, I, land, and argument of creation. Now, how do we meet each? So, when we are specifying a target object, we are specifying all these five elements together. How do we? They have to be met all at once, right? So, how do we meet all these five elements in one? Okay. A, the size of your it is purely a function of your terminal altitude and velocity. Size of the object is purely a function of terminal altitude and velocity. Eccentricity is also a function of your terminal altitude and velocity. Okay. I inclination. What determines the inclination? We are talking about the planar scale. It's not like we are after lifting off. We are correcting the inclination where we are going off the plane. That is a different concept. Yeah, we can do that. But I'm talking about the planar scale. So not changing the plane. After lifting off, we are just heading that same. Okay. What determines the the inclination? Uh, just pardon me if I'm committing mistakes in this equation. Basically, the idea of the solar system cos I and this is equal to cos latitude into sine theta. Okay. Basically, the inclination that you can achieve in case of a planar motion is a function of the latitude of the launch point and the direction in which the launch is. Basically, say we have a launch pad here. The azimuth measured from the north. Okay. Latitude, of course, right? These two determine the inclination. In that case, what will be the minimum inclination you can achieve from the given launch pad? Say the latitude longitude is given. What is the minimum inclination you can achieve? It is nothing but the latitude. You cannot, in case of planar motion, you cannot achieve a latitude. You cannot achieve an inclination like it's less than the latitude distance. Okay? Provided you fly in 90 degrees. Right? Because here you have the Earth. The Earth has to move around the equator. It's not like you cannot have normal legs, right? That is not possible. You can only have normal legs. You know limitation. So the minimum inclination that we can get is driven by from where we launch. Okay. Then of course we launch equatorial orbits. We launch spacecraft in equatorial orbits, but that correction happens in flight. We are doing an out of plane movement. That is how we achieve that. Okay. So again, yeah, there is another the capital omega. Capital omega is right ascension of the ascending node. This is the longitude of the ascending node. How do we achieve a longitude given longitude of ascending node? That is determined by the launch time. When do we launch? Your launch time is very critical in achieving the longitude of the ascending node. So that is why we launch at midnight, we launch early in the morning, late in the evening. That is because all these missions are having a different longitude of ascending node required. It is determined by the I5. Then again, AOP argument of gravity. It is also determined by the targets. I mean, the injection space, that is velocity or altitude by the so normally it doesn't mean anything. It doesn't describe the orbit. It just describes where is the spacecraft in the orbit. We are not really concerned where the spacecraft is in the orbit at the time of injection. As long as we get the orbit, it is fine. Okay. So we have the targets now. Now let us look. These all these targets still manifest as qualifications. Otherwise, terminal conditions. Okay, when we are trying to solve the optical control problem. Now let us look at what are all the other constraints. Okay, so we'll go stage by stage. In every stage, there is a set of constraints. Let's start with the first thing of this. What is the first thing? First thing, when a launch vehicle lifts off from the launch pad, what is the first constraint? It has to clear the launch pad. Right? You cannot afford to have any looper unless and until this launch vehicle has cleared the launch pad. You cannot have. So no pitching up until an altitude of 100 degrees. 300 that's it, right? That's it. Now comes the parameter that we have to optimize in the first stage. It's called the peak economy. Initial fixing. So now this is linked to the first stage now. You cannot afford a continuous steering in the first stage because you are in the atmosphere. You have a lot more to. You cannot afford to have continuous steering in the first stage. What we do is we steer for initial few seconds up until a point the dynamic pressure is not significant. Okay. Once the dynamic pressure is significant, we have a lot more handle. Steering is not a priority. So whatever steering we are doing, we have to finish it before that. The max fuel or no steering. Okay. So that is the key rate. It usually starts as soon as the vehicle covers the launch pad. It goes ahead. Kick rate is nothing but here you will see, yeah, I have to operate so the not at all. Right? But usually what we do is for the sake of getting smoother commands, we will always theta up. So you can get theta very quickly. Right? So this kick rate at the initial stage actually determines the target that we are going to achieve at the end of the stage. You have to achieve the steering by the time the kick is over to achieve whatever any stage is. That's where the kick comes. Okay, the initial kick rate comes. That is the only optimization we do in the first stage. Okay, even though I'm talking about in stages, the problem we are solving is not stage by stage. That is not possible. You have to solve the problem all at once, all stages at once. Okay. So once kick is over, then we have the most important constraint, the structural knowledge. Okay, we are in the atmosphere. So obviously there is dominant aerodynamics. Aerodynamics is dominant. What do aerodynamics do? Aerodynamics is imposing a load on your launch vehicle. You see, launch vehicle is a highly flexible vehicle. It's not as sturdy as it looks. Okay. It's like a long stick. Okay, and it has flexibility. So it cannot take too many zones. Okay, it will break. We cannot afford to strengthen the structure as well because that will have a direct impact on your vehicle. We are increasing the mass of the vehicle at the cost of kilometers. Right. So you have to design the structure as light as possible. Then whatever structural load that may happen during the atmospheric phase have to be handled in the mission design. Right. So what do we do? Basically, what are structural loads? They are lateral loads. Right. You have the vehicle going up. The aerodynamic forces are acting laterally. Right. To be tackled. You might have heard, you might have seen the SpaceX launches and all. They will be talking about max Q. What is the significance of max Q? It is nothing but the structural load. Vehicle is under a lot of pressure, and it is a critical phase of the flight. What SpaceX do or throttle engines do is they throttle down. They throttle down so that basically what is structural load? What is structural? It is the constraint can be represented as Q alpha. Right? Q is half rho v square dynamic pressure, and alpha is the angle of attack. Now, the Q by throttling down the vehicle, what you are actually doing is you are reducing the dynamic pressure during when the density is significant. Right? After that, you can throttle up and you can go ahead. But in case of non-throttleable engines, the problem is that we don't really have a handle on the dynamic pressure. Then we have to address the problem by choosing alpha. Right. What do we do there is called the gravity turn method. Gravity turn. Gravity turn, the term can be disputed. It's not like we are turning the gravity or anything. What is actually we are doing is we are aligning the vehicle along the relative velocity. What does it mean? Alpha is going to 0. Your vehicle is aligned with the relative velocity. Alpha goes to 0. Those are all going to be easy as long as you don't have an alpha. Right? Q alpha will be well within the limit. That is what we are doing. But what is the consequence? When alpha goes to 0, what happens to speed? You can see gamma dot, when alpha goes to 0, P by M sin alpha goes to 0. The lift is also not there, CL not is 0, it will not be there. Your gamma dot can be written as minus G by V first law. And your V dot, yeah, minus G by V first law. That means the point to be noted is that thrust doesn't have a role in rotating the velocity. Gamma dot, the thrust term does not count. And cos alpha is 0, thrust is completely upright along the velocity. Isn't that optimal? That is the optimal thing to do. Like you don't, gravity is actually taking the job of rotating the velocity. Basically, what are we doing? We are lifting off from the surface of the Earth. Then we are rotating the velocity vector to achieve a flight path angle of 90 or 0 degree, depending on where you measure it. Right. But there is no thrust acting in the process of rotating the velocity vector. That indeed is optimal. And hence the name gravity turns. Gravity is actually turning the velocity. So that is how we address this constraint called the structural load constraint. And there are a lot of issues there. Like what information do we have about the relative velocity vector? It is not just the thrust, right? There is a major perturbation called wind. We don't have a handle on the wind, right? So usually we do this thing called DOA, day of launch. Basically, we measure the wind uh, maybe an hour or two before the launch. Then with that we optimize the drive so that the dispersion on the wind will be less. And uh, yeah, that's the thing. And mostly in first stage we will be having open loop steering. If we had a closed loop steering, that's a different scenario. So that's the thing, right? So the dispersion wind is there, but anyways, as long as we are talking about the mission design, this is what we are doing. We are trying to make the angle of attack 0. Now, what are the other constraints that is coming? There is one constraint called stage impact, which I think we all will be at least familiar with it. See, we are having a multi-stage launch vehicle. At that time, you have exhausted the fuel of a particular stage. You have to discard the stage. You cannot take it forward. That will again will be having an impact on the payload. So you have to discard the stage. So you cannot discard it so that it goes and falls on a landmass. That is another constraint. You cannot have any wild steering weights. The steering weight should be well controlled. That is another constraint. Then we come to the second stage. So what are the phases in the second stage of the flight? One major thing is the payload fairing separation, the heat shield separation. The heat shield, the hardware which is actually protecting the spacecraft has to be discarded because we are almost outside the atmosphere. Now we really don't need the heat shield, so it can be discarded. Now where do we discard? You cannot discard it at any point. Your altitude should be sufficiently high so that the aerodynamics is less, so the heating is less. Okay, that is another constraint. Then you cannot have any rates during separation. Then it will have impact on the separation. There will be recontact. So you should be having a very benign rates during the separation events. Uh, and this image impact constraint is very critical when it comes to the second stage. Because first stage is still okay. You will be close to the mainland from the place the launch happens. And more or less it will be sea, so impact will be happening in the sea. But that's not the case for the second stage. There may be land masses there. Right? So you cannot discard the second stage wherever you want. You should make sure that it doesn't go and impact on a landmass. That is a very important constraint.
So usually what we do is we have this coasting phase. You might be familiar with the coasting phase, right? The coasting phase need not be there for all launch vehicles, but only for particular launch vehicles we have this coast phase. What is coast phase? Any phase of the launch vehicle where there is no thrust is coast phase. You are actually in a you are traveling in a conic. Say the separation happened here, then you are actually simply ascending along the suborbital ellipse. Right. During that phase, what is happening is actually your energy has to be conserved. So what is basically happening is your kinetic energy is being converted to potential energy. Otherwise, at the expense of velocity, you are gaining altitude. Why? Why do we need coasters? I can give various explanations to that. One major explanation is that this rocket stages will be having tail of thrust. So the moment you are separated, still the engine may be burning. Then you ignite the ongoing stage, but thrust is not sufficiently developed. What will happen? There can be a recontact. So you cannot separate the stage at that point. You have to separate the stage only at a point when the thrust has settled. That is one. Another reason for posting is you want favorable ignition conditions for the ongoing stage. You cannot ignite the stage wherever you want. It has to be a favorable condition. See, basically, what are we doing? We are gaining altitude, we are gaining velocity, right? So your energy is spent for both these activities, gaining altitude and gaining velocity. Gaining altitude means you are firing against gravity. Gravity losses are there. You have to minimize the losses. So it is always better to fire along the velocity vector and we get altitude gain for free. Right? So what we do is we inject the second stage injects the ongoing vehicle in a suborbital ellipse in the ascending leg. Okay, the vehicle goes up on its own, and when the altitude and velocity the states are favorable, we ignite the ongoing stage. That way, we get the altitude gain for free. At the expense of velocity, yes, it's actually gained in the ongoing stage, but altitude gain is more expensive than velocity. So that's about the post phase. Now we have come to the terminal phase. Terminal phase, the last stage of the launch vehicle, where actually the injection of the spacecraft happens. Now, if you see in all the lower stages, we don't really impose this concept of optimality. Mostly, if you see the first stage will be a solid state, where you cannot have a mass advantage. Right? Whatever fuel that you have loaded have to be spent. So there is nothing you can save in terms of mass. Then when it comes to second stage also, even though it is a liquid stage, we have this flexibility of saving fuel. We usually go for fixed duration jobs. We keep the additional fuel margin and go for fixed duration. What the additional fuel that we are having is to cater for the dispersions during the flight. That is not part of the mission. It is just a reserve fuel. Okay. Now, when we come to the terminal stage, this is the point where we actually impose the concept of optimality. Here, the burn is not fixed duration. The moment you reach the target, you cut off the engine. So it is important that you minimize the burn duration because it is not a throttle engine, your mass flow is constant, your m dot is constant. So minimizing integral m dot dt is same as minimizing integral 1 dt as long as your m dot is constant. Integral 1 dt is nothing but time, minimum time. So you have to minimize the time of flight during the terminal stage. Okay, we have, you might have heard this during the telecast of launches. Not in all vehicles, but in some vehicles we have this phenomena. The vehicle actually dips, especially when it goes to GTO orbit. After the payload separation or during the terminal stage, the vehicle slightly dips. And there is a chance that it may re-enter the atmosphere, but the HV has already been discarded. So the heat load on the spacecraft may increase. So we cannot afford that. We cannot move the spacecraft at any cost. All this exercise is to save the spacecraft. Right. At that point of time, we impose a heat load constraint. That the heat load on the vehicle, basically it's an ultimate constraint, cannot go below a particular value. That is another constraint. There are a variety of constraints we will see when it comes to launch vehicle mission design. To name a few, there is this: how long can you have a launch vehicle mission? How long? You cannot have a very long mission, especially launch vehicle. Satellite is a different affair. You cannot have a very long launch vehicle mission. It is restricted by one battery, power availability. See, all your avionic packages on the launch vehicle has to be powered by batteries, right? You cannot. There are no solar panels or those things on launch vehicles. So it is battery. So battery cannot supply power for a long time. Another interesting thing is visibility. See, the entire flight of the launch vehicle should be visible from the ground station. You cannot afford to have ground stations all around the world, right? So, all major events should happen well within the visibility. That is another reason. The reason you cannot have a prolonged rocket mission. Satellite is different. Okay. Uh, so that's yeah. So you get a fairly good idea about how we have to formulate the launch vehicle mission design problem as an optimal control problem. I have discussed the objective, the dynamics, the various constraints. Now, yeah, you have to put all these constraints into mathematical equations to solve it. That is there. And again, the biggest challenge is to solve this problem. Formulating is not everything. You have to solve it. So, what all methods you adopt in solving an optimal control problem. It is not a problem that you can solve by hand. For that matter, any optimal control problem, unless you satisfy a very nice performance index, a very decent system dynamics, you cannot solve it by hand. You have to depend on numerical methods towards solving the problem. What all numerical methods can be adopted? uh, there is this classical calculus of variation methods where you formulate the entire problem as a 2-point boundary value problem. Then you can use all numerical methods like shooting methods, steepest descent, Fossey linearization, whatever. You can make use of all that, but then you will be able to solve this problem. That is going to be a humongous task. It is not possible, at least in my knowledge, limited knowledge, it is not possible to solve this problem using classical calculus of variation techniques. Then we depend on direct direct methods, otherwise called transcription methods, where we make use of collaboration techniques. It is basically reformulating an optimal control problem to a finite dimensional non-linear programming problem. So it becomes an optimal, from an optimal control problem, it becomes an optimization problem. There you can apply all kinds of optimization techniques to solve the problem. Those are various aspects of solving the problem. Briefly, I will discuss the re-entry missions as well. Re-entry missions, how are they different from launch vehicle missions? Yeah, one is going up, the other is going down. What are the different kinds of re-entry vehicles that has flown over the time? Can you name a few? You can broadly classify it. One is capsule. Capsule which we have. Shuttle, yeah. Generally, generalize space planes, right? Space planes and any other class. There is a reason in it. Spence stages, very interesting re-entry. Spence stages. These are broadly the re-entry vehicles, and how do we design their missions? Okay, all these are different. The mission design is also different. Their constraints also different. Capsule, say the control we are having, there are no aerodynamic surface. It is not a flying wheel. It is a stone. So what are the controls that we have? Band control. We can modulate the lift and somehow meet the targets to some extent. Then we have shuttle like space planes, where it is no less than an aircraft, where you have all kinds of aerodynamic surfaces which you can modulate, you can fly, but unpowered. Okay, that is there. Then yeah, this re-entering space stage is a very interesting problem. not just in formulation, there are a lot more challenges when it comes to re-entry spin stage. See, there are multiple burns here. I don't know whether you have observed when a spin stage, SpaceX like vehicle, Falcon vehicle, when the spin stage separates, uh, there are three burns. First burn is called a boost forward or a boost backward. That is primarily to adjust the range. You have to cover a certain range to go and land at a designated location. Right. So the boost back or boost forward, depending on where you are heading to, the boost you have to optimize the burn duration. The not just the burn duration, the attitude of burn, all those things. Then we have the re-entry. You are coming back with a very high velocity. Now with that kind of velocity, if you enter the atmosphere, then the heat load will be very high, right? So you have to decrease the velocity. You do a re-entry. Then it has aerodynamic surface as well. You would have observed it has grid fins. So during the re-entry phase, it actually deflects the grid fins and has a very good control over the range. Then when it is just about to touch down, we have this landing one. We have this landing one, which helps you to find your landing point, also to hover to some extent. And then so beautiful to see a rocket vehicle coming back from space, an altitude of about 110 kilometers, comes back and hovers, and it is smoothly touches down at its landing pad. So those missions are really not just beautiful to witness, but really interesting to formulate and solve as well. Then considering manned missions, I am not talking about manned missions. But when it comes to manned missions, there are even more constraints. You cannot come down with any acceleration. That is the biggest constraint because you have human beings on board. They cannot tolerate any acceleration. There is this concept of exposure time. Right? You will be familiar. You might have seen this in many Hollywood movies and all. A fighter jet pilot experiencing an acceleration of about 10 g. You can see how his face gets, So knowingly, you cannot send an astronaut to such kind of extremes. Right? So you have to arrest the acceleration with which it comes down. Again, which axis the acceleration is acting, all those things are there. Usually, any human being can tolerate a very high acceleration, provided the time duration to which he is exposed to is well within the limit. And this convention is that 4g, that is 4 into 9.82 meter per second, any human being can tolerate for indefinite time. Anything beyond 4g, there is a time attached to it. So you cannot exceed those limits. Those are the constraints that we have when it comes to manned missions. Then again, you cannot fly any bank angle because again this bank angle will have a effect on this G because effectively you are reducing the lift and contributing towards side force. So it will have an effect on the acceleration. Your drag will be more. The acceleration levels the capsule is experiencing also will be very high. So these are the two constraints I want to talk about when it comes to re-entry vehicles. Okay, yeah, so that will be all about the mission design for today. In case you have any doubts, I'll be happy to answer if I can. Good. All right. Yeah.
Did you talk about that phase, like terminal phase where you continue not able to have why
Okay. I'm not sure why that happened. Actually, it is an outcome of the optimal trajectory. To put it into perspective, I don't know, maybe I'll call it like the gravity when the dip happens. The gravity is also assisting you in gaining the velocity. Right? Yeah. It is particular to some vehicle. It's not like it happens in every vehicle. Also, the dynamics of the vehicle, the sizing of the vehicle, all those things plays a role there. So, yeah, that will be all with respect to launch vehicle mission design. I hope, yeah, please. Yes, 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 yes. Basically, collocation method is what we are using. Basically, what it does is you have this differential equation. This differential equation can be represented using some approximations. That is what basically collocation is, right? So you will approximate each and everything, the performance index, the constraints, everything in terms of some basis functions. It can be Chebyshev functions or Legendre polynomials. Some basis functions you will represent all these constraints. Then you will be solving for all these constraints only at particular points, not all along the result. Basically, in classical calculus of variations, we will be solving all along the curve. But when it comes to transcription methods, we will be solving only at certain points. You again, you have the flexibility of choosing the points. What sort of points I want to pick? How many points I want to pick? All these are flexibility depending on how uh, how well represented your solution. To name a few, there is the pseudo-spectral methods. You can of course learn about it. Then again, to name a few of the nodes, there is Legendre Gauss nodes, Legendre Gauss Laboratory nodes, Legendre Gauss Bratov nodes, LGL, all those things. Just these are equivalent representations for differential equations. How do you represent differential equation in terms of nonlinear equations? Uh, Okay, to talk about my career journey, I did my schooling and everything. Schooling in Kerala, Palakkad, that's where my hometown is. Then I did my engineering, BTech in Electronics and Communication Engineering from Government Engineering College, Thrissur. I got placed uh, by the end of my graduation, by the end of my uh, college days, to a tech company, a software company, Oracle Financial Services. So I had a very short stint in Oracle Financial Services. I was working on bank development of banking software. So I was a backend developer there. Then at some point I realized that that's not exactly what I want to pursue as a career. Then I, without any further plans, I one day I dropped, resigned from the job. Then for about a year, I had nothing to do. I was jobless. I was actually preparing for competitive examinations. My thing was that I wanted a job was a managerial role. So that's what I was aiming for. I was actually preparing for engineering services. I couldn't make it. Before that, I got into ISRO through ICRB. So I hope you are all familiar with the recruitment process in ISRO. There are various avenues actually. One popular thing is ICRB, where the organization conducts a test followed by an interview. They will be declaring vacancies. You people can apply, appear for the exam, then followed by the interview. They will be declaring the results. Then you can come and join. That recruitment happens in undergraduate level. So the qualification is BTech. So that usually, if my knowledge is correct, the recruitment happens in two steps. Okay, for electronics, mechanical, and computer science, one notification will be released. The other notification for I think civil, electrical, and air conditioning. Then that's how BTech people join the organization. Then there are opportunities for MTech students. I'm not sure whether a central level recruitment is there for MTech, but definitely I mean, not a central level, but center level recruitment is there. That is, there are various centers under ISRO. Right? There is VSSC, there is URSC, there is NRSC, there is SDSC, Shashri. So all of these organizations, all of these centers, they will be publishing notifications demanding candidates from having an MTech specialization to come appear for an exam followed by an interview. That is another avenue. Then There is for PhD people, it is to my knowledge, it doesn't happen quite often, but I think there is a direct where you can, after completion of PhD, you can enroll, and if an opportunity comes up, you will be asked to come give an interview, and then you will be recruited. Uh, yeah, so that's the doors open for you for any engineering graduate to be a part of Indian space program. Life at ISRO, it's great. I must tell you that. Even though I was expecting a managerial role, then only after joining the organization I realized that this is as enjoyable as any manager or any job could be. Right? You will be invested. Depending on your placement where you are designated to work, you will have multiple responsibilities, not just technical. If you are working for a particular project, particular launch vehicle project, I can only talk from VSSC standpoint. If you are working in any projects there, then your role is equally managerial and technical. You have to take care of a lot of technical aspects. At the same time, you have to take care of a lot of managerial aspects like schedule of launch, organizing the launch part. A lot of things to be taken care of when it comes to a project. When it comes to a technical development kind of job where I belong, uh, you will be exposed to all kinds of problems. I belong to the guidance design division where I design guidance algorithms for launch vehicles, for developing launch vehicles. So there you are exposed to a variety of technical problems where you pose the problem, you solve them on a day-to-day basis, and you have a lot of exposure in terms of gaining knowledge. Every day is a learning, definitely. You will get to learn from not just textbooks, but from experts. It's not going to be a classroom experience, of course. You are pretty much on your own, but at the same time, there are a lot many people to help you, support you, clear your doubts. That kind of an atmosphere is very interesting, very enjoyable. Then, yeah, you get to be part of prestigious missions. Yes, that is there. You get to share rooms with eminent personalities, right from chairman and like I can name lot many people. You get to share not just the space, you can have great conversations with them on technical stuff. You can ask your doubts, they will be more than happy to clear your doubts. Uh, and if at some point if you feel like I have graduated in a particular field of study, then there are a lot more fields available to you to explore. If somebody says that he is an expert in control, if he believes that he has excelled in control, then he can go and learn structure. If somebody believes that they are graduated in structures, they can go learn propulsion. And if somebody believes that they have mastered propulsion, they can go and learn software. So it is interdisciplinary. I myself had this. I am coming from an electronics background. All I knew was circuits, but I never worked with circuits after joining the organization. I had a great learning in terms of control system, optical control, flight mechanics to some extent, uh, software. Yes. So you are being exposed to a variety of topics. That's the best part of it. Of course, you grow in the organization in knowledge, in designations, and you. Uh, there is one thing that I must say: the respect that you gain in the society. I have no words to express. Everybody will go in awe. If somebody gives that you are working in space research, that's something that cannot be matched. Uh, and yeah, there is this popular belief. I don't know. I don't believe it is true that IITians don't generally join Indian space research. I don't know. I have never felt so because I have many colleagues from prestigious institutes across the country. But again, if at all any truth is there, it is an opportunity for you to correct it. Right? You all can have you all of you have an equal opportunity to come and join the organization. That's the best part about the organization. So I really urge you, to break that belief, if at all it is there, and come join the organization, contribute towards Indian space. That's all I have to say. Thank
So when is the best time to join?
you. Earlier the better. That's what I was. Earlier the better. Yeah.
Terms of opportunity.
Opportunity, like it is equal. There is no like if a person joins in terms of age or educational qualification.
Like before gaining specialty, then joining is better. Or, like,
I agree that okay, you can get a master degree and then join. You will be having certain advantages that is there. But I have always felt that the earlier the better. If you are joining after BTech, immediately after BTech, not like after 10 years after BTech, because the age is also a factor. Learning happens. It's not like you have to come with a particular skill set. It's not like that. You will get to learn. People will ensure that you learn and you apply your knowledge to whatever that can be implemented. That's how things usually happen. So earlier,
why ISRO won't allow aerospace engineers to write the exam?
no, I cannot comment on it.
What's the problem?
No, no. I don't know, Arshan, actually. I don't know. There must have been some thought process. SSL. Definitely. From the day I joined, I have invested most of my time in the organization with SSL. It's not a vehicle, it appears to be. Uh, Three rocket stages stacked one over the other, solid states stacked one over the other. There is no launch vehicle existing in the world that can inject spacecraft as accurately, to my knowledge, as necessary. So the kind of work that has gone behind it is too high. As far as the launch rate is very simple. Solid stages are easy to manufacture, easy to assemble, easy to maintain. But when it comes to vision, the complexity in the software is very. So if you are able to achieve missions with high precision necessarily, that is very recommendable. I most of my work has gone into this, so I would definitely say.
Can we expect normal working hours?
It's not a difficult government. You have to work late in the night sometimes, yes. Be prepared for everything. It's not a typical government job to go like 9 o'clock in the morning, you come back after 5, nothing else to think about, worry about. It's not like that. Sometimes there will be challenges that you have to invest more time in the office. But again, you will enjoy that time, is what I'd like to say. Every moment you will enjoy. Thank you.
And see. And this. And
Yes, just wait a second. We have some refreshments as we have promised. So if you want, you can just take us and you can enjoy. So what? Yeah.